talk about more about the cross product. Again, this is somewhat like what's in the book, but I have a different perspective on it. What I ended with last time was that the cross product is a vector perpendicular to the plane made by u and v. It's easier to just say it's perpendicular to u and v. And with magnitude equal to the area of the parallelogram made by u and v, and satisfying the right-hand rule. And that's the trickiest part, but it's not the most deep part, really. So let me just go ahead and let's see. This one, you can say, more specifically, this is magnitude of u, magnitude of v, sine of the angle between them. So let me do a real quick example. Suppose I know, here's some axes, and here's a vector u, and here's a vector v, and I'm given that the magnitude of this guy is 4. I'm given that the magnitude of this guy is 8. And I'm given that the angle between them is 30 degrees. It's a little bit more than 30 degrees, but it's plausible. Okay? So, u cross v. Let's see what I can say about u cross v. If I don't say anything more about exactly what these vectors are like, I can't exactly nail down the vector u cross v. I can draw a picture of it by using the perpendicularity and the right-hand rule. It's going to be going in which direction? Well, u is supposed to be my hand, and then my fingers curl towards v. And again, if I put a copy of v up here, I'm going to make the parallelogram. There's a copy of v. If I put them tip to tail, that's when it's easiest to use this rule of the hand is u, the fingers are v. Okay, it's going basically sort of into the board, it looks like. So there's going to be a vector going in that way towards the board, towards the negative x-axis roughly. And that's going to be the direction of u cross v. Well, what's the magnitude of u cross v? I can get that. It's 4 times 8 times sine 30, and I picked that to be easy. 4 times 8 times 1/2, 16. So it's going to be a rather long vector compared to these guys, going way back out in this direction. Something like that with u cross v. Now, the only way I'd be able to make that really precise is if I knew more about the directions of u and v, if they were like along an axis or something like that. And there's a nice problem in the book about that. The main thing is that if I don't have the components for this, I have to use the geometric formula in some way, the geometric characterization about perpendicularity and the magnitude formula. But I want to lead into how we would get the component formula. So let me tell you a story that leads to that, as opposed to just dropping it on you like the book does, which is pretty typical of a textbook. Let's just do a few special cases of cross products. What should I cross j be? That we can figure that out completely, precisely, but just using the geometry. It's supposed to be a vector that's perpendicular to I and j. Well, it must be in the k direction or the minus k direction. And its magnitude is the area of this unit square. That's the parallelogram that they form. So it's either plus or minus k. Okay, notice I'm putting these little hats over my unit vectors because it's often a way to remind ourselves that they're special, that they're unit vectors. You can put arrows over them and it'd be fine. And let's just use the right-hand rule. I coming out, j going to the right, and k is going up. So it's just actually k. Similarly, j cross k, that's again, the area is a unit square. It's perpendicular to j and k, so it's either plus or minus I. And j, k I, so it's plus I. And then k cross I, I've got k, and then I, and j. I picked those all very specially to get pluses. The way to remember that is if I put them in a circle, I, then j, then k, then I, then j, then k, then I, then j, then k. That's when you get the plus signs. And remember, one of the things I think I mentioned in the other video is that in general, if I switch the order of two vectors, I get a minus for the cross product. That doesn't come from the perpendicularity part, it doesn't come from the magnitude part, it comes from the right-hand rule. But it turns out to be very, very crucial to make everything work. And it's very related to the fact that when you switch two rows into determinant, you get a minus sign. It's really the same fact. So that means that tells me, for example, j cross I is minus k, etc. So that tells me what k cross j and I cross k are going to be. So that's pretty nice, okay? We've got some building blocks. If we knew some good algebraic properties for the cross product, we'd be good. Well, here's the analog of the commutative law. It's not exactly commutative, but it's skew commutative or anti-commutative. Well, what else? Let's see. There's a very nice fact that you can get out of the geometry, which is that, and this is going to be very reminiscent of what been doing with determinants. If I take u cross v, and then I scale up u, so that's going to make this parallelogram k times bigger. I haven't changed the direction, so I'm not going to change the direction of the cross product. I haven't changed any orientation, so the right-hand rule isn't going to give me anything different. I'm just making the area k times bigger, and so this should be a vector in the same direction as I started, but I'm just going to scale it up by k. Now let's see, what if k were negative? If k is negative, it flips this way. Like if it's -1, I get the same area, but now the right-hand rule is going to give me the opposite direction because the orientation of this guy has been flipped. Hey, that's cool. That's telling me exactly the right answer. If I flip one of the vectors, the right-hand rule is automatically telling me that I'm going to flip the cross product. That has a lot to do with why this has to happen, why the right-hand rule has to work the way it does to make this rule work even for negative k. And we saw that when we first started doing determinants, we had a rule that didn't seem to work. It was like this, but didn't seem to work for negative k. But when we put artificial seeming minus signs everywhere, like the right-hand rule seems artificial, everything works nicely algebraically. So that's going to be really useful because it allows them to have more general building blocks. So for example, 5i cross 3j, it tells us we can take the 5 out, and pretty clearly we can take the 3 out, and so that's going to be 15i cross j, or 15k. But the real big rule that we'd like is what happens when you combine things. Can I do something like I plus j cross j plus k? And here's where we might want to have a little faith in the notation. Not a great reason to believe something, but they're calling this a product. They're not calling this the vector that denotes area, or the thing you make out of a parallelogram in three-dimensional space. They're calling it a product. You never, ever, ever in mathematics call something a product unless it satisfies a distributive law over something called addition. If the addition is present. If there's a multiplication and addition, you wouldn't call multiplication or a product without having a distributive law. And so what they're suggesting with the nomenclature is that it's not just some random geometric operation, and it doesn't just satisfy a few nice algebraic properties, it's going to satisfy the distributive law, so we're going to be able to FOIL this out. So let's have faith in that for a little bit. I cross j is going to be k. I cross k is going to be, let's see, that's the minus version of that, so that's minus j. J cross j, ooh, what's j cross j? I don't think I've really talked about that yet. Well, let's see. Any vector cross itself. What's the angle between those? What's the area of the parallelogram that's created? It's 0. And so it's just the 0 vector. That is a fundamental thing about cross products. And it's very different from squaring a number or taking the dot product of a vector with itself. This is the only kind of product we've seen where taking a product of something with itself always gives 0. That's bizarre from our point of view of numbers, but it's a very important property of the cross product. So j cross j isn't going to contribute anything, and j cross k is I, and I get an answer. So it's this distributivity property, it's also called a linearity property, that we're going to assume is true, and it's the one thing that we don't really know how to prove geometrically yet. But it'll allow us to take the cross product of any two vectors. Okay, let me see if I'm over. Okay, now, so, let's see. So I'm going to use these building blocks and things like I cross I equals 0. That's another kind of building block, because it's a vector with itself, that allows us to take the cross product of any two vectors. So the long way is like this: 5i plus 3j minus 2k cross 2i minus 7j plus k. And I'm just going to FOIL it out. There's going to be, in principle, 9 different terms, but anything in the form I cross I is going to be 0. J cross j is going to be 0. K cross k is going to be 0. So I'm just going to ignore them. I'm going to do the other 6. 5i cross minus 7j. I get minus 35. And then I cross j, I look it up, that's k. I and k, so 5i cross k is minus 5j, because that's the negative version of this guy. 3j cross 2i, so that's going to be minus 6k, because j cross i is in the wrong order. It gives me a minus k. J cross j is 0. Then I get 3j cross k, so that's plus 3i. Then I get minus 4k cross I, that is the right one, but I already have, that's a j. I already have a minus sign. And then k cross j, I have 2 minuses, so it's 14, but k cross j is backwards, so it's minus 14i. Hopefully I'm doing that right, even though I'm doing it in my head at the board. And then I just collect. I get minus 11i, that's these guys, minus 9j, and minus 41k. They happen to be mostly all minus. Interesting. Okay. So that's not a terribly inefficient way to do it. You just actually calculate this out, just assuming this one crucial property that we haven't really proved, the distributive lie. Okay. Now, the book talks about how you can phrase this using the language of the determinant of a sort of a weird special 3x3 matrix. And we'll definitely talk about that, and obviously there will be a connection to what we're talking about with determinants. But, and you can definitely use their formula, organizing it like they do in the book. But if you want to, you can do it this way, and I'll tell you, it doesn't actually take much longer at all. And it's, in a way, it's actually more secure because you're only using these building block rules and the assumption of distributivity.